Hello there, my friends. For today's lab, we are going over the concepts of slew rate and the offset voltage of op-amps. First of all, let's see what's the slew rate. For any op-amp, if you apply an input, for this example a square wave, the output will not immediately go to the maximum voltage value like this. It's the desired output, however, in real life, the output will be like this. The unit for slew rate is volts per microseconds. For instance, if a slew rate is given as 1 volt per 1 microsecond, the output will become 3 volts after 3 microseconds have passed. So for this graph, for 10 volts of maximum voltage, it will take 10 microseconds. So let's see our circuits. In circuit 1, we apply 10 volts of square wave with frequency 15 Hz for LM741 op-amp. Let us see the results. As you can see, the yellow shows the input and the blue one shows the output. Volt div for yellow and blue is 1. Each square is equal to 1 volt vertically, and time div is 1 microsecond. So each square is equal to 1 microsecond horizontally. So let's see, for this region, for this block, let us count the squares. 1, 2, 3, 4, 5, 6. 6 squares in the horizontal region and 2 squares in the vertical region. So that means it will take 6 microseconds for the output of the op-amp to reach 2 volts, and it is 2 volts per 6 microseconds. So the slew rate is 1/3 volts over microsecond, which means 0.33. It is the slew rate for this op-amp. So, in conclusion, in order to meet the requirements, the slew rate should be very big. Bigger the slew rate gives the better performance. So for the square wave, here's our period. To make the op-amp reach the maximum voltage value, like this, and reach the minimum voltage value, like this, for this example 0 volt. For this example and for this op-amp, we have the slew rate as 0.33 volts per 1 microsecond. It should be bigger than 10, which is the maximum frequency, which is the maximum voltage, times 2. This 2 is for increasing voltage and decreasing voltage, times frequency. So 0.33 times 10 to the 6. I converted it to seconds. Should be bigger than 10 times 2 times f. F should be smaller than 16,500. Let's see. Yes, as we can see, it is at the limit. If you try to push it through beyond its limits, if you give a much bigger frequency, such as 20 kilohertz, it cannot reach the maximum and the minimum voltage values. The output now cannot represent the input signal perfectly. In this example, it reached the maximum voltage, however, it cannot reach the minimum voltage. If you apply much smaller frequency from the input, now everything seems fine. The input perfectly overlaps with the output. Almost there is no difference. It is perfect. If you try to apply much bigger frequency from the input, as you can see, we start to lose the output signal. Okay, maybe we are just applying limit frequency from the input. Okay, it can reach the maximum value and reach the minimum value perfectly. However, the output signal does not overlap with the input signal. What if we increase the input voltage at this time? Again, it cannot reach the maximum or the minimum value of the input signal. So what about the sinusoidal signals? For circuit 3, we are applying 5 kHz of sinusoidal signal. Amplitude is 10. Here's the formula for the sinusoidal signals. Slew rate should be bigger than 2 times pi times with maximum times f. 0.33 times 10 to the minus 6 should be bigger than 2 pi times 10 times f. F should be smaller than 5254 Hertz. Don't forget, the slew rate, actually the frequency that we found for the square wave, was for reaching the maximum voltage value. However, for sinusoidal
signals, that formula will give the overlap limits for the input and the output. Let's see. We are just applying 5 kHz from the input. Okay, it seems it overlaps pretty good. There's no problem. However, what about 6 kHz? Now we have a problem. The output is not a good representation of the input signal at this time. For much bigger frequencies, by the way, now the output signal is completely trash. It is meaningless. So that was the concept of slew rate. So what about the offset? As we know, this is the op-amp voltage follower circuit. It follows the voltage applied from the non-inverting side. So here it is 0 volts. So we should see 0 volts at the output. However, we see 0.001 volt at the output. This is the offset, and the ambient temperature affects the offset voltage. Now, in this simulation, I cannot change the ambient temperature. I already tried these options, however, it seems they are not effective. As you can see, another non-inverting amplifier circuit. What is the gain of it? 2.6 kilo ohms over 1.8 kilo ohms, which is equal to 2, and for non-inverting amplifier we have 1 plus. Gain is equal to 1 plus 3.6 kilo ohms over 1.8 kilo ohms. Times VI times VI is equal to V out. Now we have 3 times V input. What is V input? It is equal to 0. V out should be 0. However, for this example, it is 0.003366. So, the op-amp gain will multiply the offset voltage. And maybe another example. Let's take 1 volt. And here we should see 3 volts at the output. However, we have an additional offset voltage at the output, which was multiplied by the gain. So, now, if we try to formalize it, V out is equal to V I plus V offset times AV. Okay, I think that's all for today. Thanks for watching and see you in the last lab. Thank you.